Hey, in this tutorial we're looking at section 5.6 on parametric equations. So a locus is a set of points traced out in the plane, satisfying some geometrical relationship. So the path a moving particle makes is a locus and can be described by a Cartesian equation. Cartesian equations can't tell us where the particle is at any given time. Okay, so we can often have graphs on our Cartesian plane. Okay, but we can't actually tell where our particle is if it follows that path at any time. Okay, so the path traced out can be defined by another third variable or parameter, often t. Okay, note we can describe the unit circle in terms of the parameter theta, since x equals cos of theta and y equals sine of theta. So that's an example of one that doesn't use t. We use the parametric equations x equals x of t and y equals y of t. Okay, if we can, the parameter from these two equations, that should be if we cancel the parameter from these two equations, then we get y equals f of x, called the explicit relationship. So if we cancel out our parameters, which is what we want to do, because essentially what we're going to have is we're going to have equations. We've got y and t and x and t, so if we can do a bit of rearranging and substitution, we can eliminate the parameter t to get our explicit relationship, which is usually what we want. Okay, because we know how to graph our equations, things like that. Okay, so when they're in terms of x and y. So have a look at some worked examples. Okay, so we've got worked example 19. So given the vector equation r of t equals t take 1 I plus 2t squared j for all t greater than 0, find the Cartesian equation of the path, okay, and state the domain and range and sketch the graph. Okay, so to start off with, what we need to do is define our x and our y. So we know our x is the coefficient of our I, so x is equal to t minus 1. Okay, and y is equal to 2t squared. Okay, so what we do is we rearrange this equation here and say, well, t is equal to x plus 1. Okay, and so we can put now that t value into this one. So this y equation becomes 2 times x plus 1 squared. Okay, now we need to do a little bit of thinking here. So because t had to be greater than or equal to 0, so it was greater than or equal to 0, okay, it means that our x value, okay, is always going to need to be greater than or equal to minus 1, okay, because we were t take 1. Okay, and similarly y has got to be greater than or equal to 0 as well, because this had to be greater than or equal to 0. Okay, so we've got our domain and range then. Okay, so we just need to sketch it now. Okay. And when we sketch this function, we start here at minus 1, which is the point we had then. Okay, and it's going to be parabola that comes up like this and just keeps going. Okay, where our turning point would have been at -1. Okay, and that would have been at 2. So there wasn't too much in it. So the steps were we defined our two equations x and y from our coefficients of I and j. Okay, rearranged one, subbed it into the other. Okay, just used our knowledge of what our parameter initially was to work out what our domain and range had to be, and then we could sketch it. Okay, so we'll have a look at the next part. So eliminating the parameter. So eliminating the parameter can be hard. So sometimes we need to try using direct substitution, which is what we did a minute ago. Okay, but we can also use trigonometric identities as well. So which is what we're going to need to do in worked example 20. So given the vector equation r of t equals 2 plus 5 cos of t I plus 4 sine t minus 3 j for all t larger than 0, and that should be greater than or equal to 0, find and sketch a Cartesian equation of the path and state the domain and range. So we start off in the same way, defining what x would need to be. So x is going to be 2 plus 5 cos of t, and y is going to be 4 sine t minus 3. Okay, what we want to do is rearrange these for cos of t and sine of t. So rearranging this one for cos of t, will give us x minus 2 on 5. And this one for sine of t will equal y plus 3 on 4. Okay, so this is one of the cases where we need to use a trigonometric identity. So what we use is cos squared of x plus sine squared of x equals 1. Okay, so we can square this side, okay, which will make it x take 2 squared, okay, plus our, sorry, that should be on 25, plus our y plus 3 squared on 16, and that equals 1. Okay, so you can see that we used our little identity there, okay, to actually square both of these things, and now we have an ellipse, okay, with a centre at 2 minus 3, sorry, will be our centre. Okay, so we can get working here. So we say our semi-major axis will be 5 units from here, and our semi-minor axis will be 4 units. Okay, so we can now get to work and start to sketch this. Okay, we know our centre, as we said, is at 2 minus 3. What am I doing? Sorry. Minus 3. That's our centre there. Okay, and we know that our semi-major axis in our x direction is going to be 5 units, so we're going to have to come up 5 to 7 and come down 5 to minus 3. Okay, so I'm going to come to these points. Okay, and our semi-minor axis is 4 units, so we're going to have to come up to 1. And we're going to have to come down to minus 7. Okay, so we've got all our corners, if you like, of our ellipse. So we can sketch it like so. Okay, so simply we can then say our domain is from minus 3 to 7. We can just read that off now. And our range is from minus 7 to 1. Okay, and we'll finish with that worked example. So getting there. Okay, so we've got one last worked example to have a look at. Okay, so we're looking at worked example 22. Okay, we want to show that the parametric equations x of t equals 3 on 2 outside of t plus 1 on t, and y of t equals 2 outside of t take 1 on t. Okay, where t is an element of all real numbers excluding 0, represents the hyperbola x squared on 9 minus y squared on 16 equals 1. Okay, so we need to start off just write down our equations that we've got. So we've got x of t is equaling 3 on 2 times t plus 1 on t, and y of t is equal to 2 outside of t minus 1 on t. Okay, so we want to just rearrange these a little bit. Okay, and so we're going to just think of this as x and y rather than our x of t and y of t, sorry. So we're just going to just multiply across here, so we're going to get 2x on 3 equals t plus 1 on t. Okay, and this will be our y on 2 equals t minus 1 on t. Okay, and what we're going to do is we're actually going to square both of our equations here, okay, which is going to give us, for this one, if we call that 1 and that 2, well, 1 is going to become 4x squared on 9 equals, when we square this side, we get t squared plus 2 plus 1 on t squared. That's what equation 1 became. Okay, and this one's going to be y squared on 4 equals t squared take 2 plus our 1 on t squared again. That would be equation 2. Now if we take equation 2 away from equation 1, you can see we're actually going to cancel out some things here. Okay, so if we take 2 from 1, okay, then what we're going to get is we're going to get our 4x squared on 9 minus y squared on 4 equaling 4, because our t squareds are going to cancel out, our 1 on t squared is going to cancel out, 2 take negative 2 gives us positive 4. Okay, and just a little bit of rearranging, we're getting rid of our 4 here. That means that we're going to get x squared on 9 minus y squared on 16, if we're dividing everything by 4, equals 1. Okay, which is what we need to show. Okay, so look, the parametric equations don't have to be horrible, so hopefully you don't have too much trouble getting through the questions on this section.